This video is for the Oscillations, Nuclear Physics and Thermal Physics, ISP, which is part of Unit 5, A2 Edexcel Physics, and this is going to go through Task 1. Okay, so Task 1 is all about the idea of oscillations, simple harmonic motion and resonance, essentially. If you want something to look back on in terms of AS, definitely look back on waves, definitely look back on the idea of Hooke's law. If you want something to look back on in terms of A2, that will help you out. Circular motion is key to this area as well. So let's have a look at our explaining everything tasks. So they want a description of simple harmonic motion. So I would certainly draw a distance, velocity, acceleration, time graph for simple harmonic motion. And they're very straightforward in the sense of what each one is a differential of the one before it. Okay, so these will come up in the questions that are coming up, so I won't go through that in that much detail right now. But it's pretty straightforward in terms of graph thereafter. Okay, so this is the differential of that, and this is a differential of that. Okay, so sine, cosine, minus cosine is the perfect example of what's actually happening there. Sorry, sine, cosine, minus sine is the perfect example of what's happening there. The conditions required for simple harmonic motion. Okay, so the idea is a force always acts in the opposite direction to motion. Okay, the force is always trying to return it to the equilibrium position. Force is directly proportional to negative displacement. That's the idea. Okay, that's the condition for simple harmonic motion. Also, you've got to remember in simple harmonic motion that the amplitude does not affect time period. And there's always this force that is trying to return you to the central position. The equations of simple harmonic motion, well, they're all listed in the equation list in the ISP, so I'm not going to list those out. An experimental method for checking whether an object is displaying, that should be simple harmonic motion. Okay, so the simple ones are ideas like a spring, a mass on a spring, which you would have done in class, and a pendulum. So make sure you have a go at describing those experiments. Right, let's get stuck straight into the questions. Oh, just to highlight them. It should be quite a bit. Yep, here are your simple harmonic motion equations. So in terms of the ISP, write those out, list them what they all are there. Remember, that's a squared. For some reason that hasn't. There we go. That didn't come across correctly. Okay, as you can see over there, if you start with cosine, it ends up being sine, and that ends up being minus cosine. Okay, so you can see acceleration, velocity, and displacement, how they're linked there. Right. Okay, let's get into these questions then. So we've got a hydrogen atom on a spring. So this is a model for the bonds inside an atom, essentially. So you've got a simplified model that ignores the vibration of chlorine atom and just considers the hydrogen atom as a mass m on a spring of stiffness k at the other end. So this is our model of actually what's going on in terms of this molecule. Show the acceleration of the atom. A is given by A is equal to minus kx divided by m, where x is displacement of the hydrogen atom. So that's pretty straightforward. We've gone through this derivation in class. So it's the idea that F is equal to minus kx for simple harmonic motion. F equals to kx is what we're used to, but F is equal to minus kx in terms of these situations, because the force is proportional to negative displacement. And it ties into Hooke's law in terms of that stiffness being the stiffness of the spring. And this force is causing an acceleration, so we can use F equals ma. Well, surely these two are equatable then, if that's the only force involved. Well, yes it is, so let's equate them. And therefore A is equal to minus k x over m. Okay, which is exactly what they're after. Hence derive the equation for T is equal to 2 pi m over k for the period of the natural oscillations of a hydrogen atom. So the idea in terms of what we've got to use here is we've got to be using our simple harmonic motion equations to actually get A out of this situation and replace it with T. So the idea is, how do we get from A to T? Well, A is equal to minus omega squared x. So if we rearrange, so if we substitute that in, you end up with omega squared, sorry, minus omega squared x is equal to minus kx over m. Well, our x can cancel out, and our minuses can cancel out. So you're left with minus omega squared is equal to k over m. Well, that's not completely useful right now, because the equation we want hasn't got omega, it's got time period. So how do we get from time period to omega? Sorry, just let me lift that up so you can see everything I've got there. Well, omega is equal to 2 pi over t. So omega squared must be equal to hold on. We're going to get a very long way around this. Essentially, all you need to do now is, sorry, just clearing a few things. If you rearrange this for t is equal to 2 pi over omega, if you then substitute your omega in from over there, omega is equal to, let me write it over. Omega is equal to root k over m. There we go. So I should zoom out on my calculator a bit. There we go. And if we substitute that in, you end up with the expression that they're after. 2 pi m over k. If you're wondering why this is flipped over from this situation, well, it's because the omega is underneath. So you actually end up with 2 pi over root k over m, which is the same as that situation there. Okay, I'll zoom in on that bit so you can see that. Probably too far over zoom in. There we go. Okay, so infrared is used in chemical analysis. Compared to other radiations, infrared has a radiation of 3.3 nanometers, so micrometers, and is strongly absorbed by hydrogen chloride gas. As a result of this absorption, the amplitude of oscillations of hydrogen atoms slightly increases. What's named this phenomenon? Increase of amplitude is all down to the effect of resonance. State the condition for this to occur. The definition of resonance is that the natural frequency is equal to the forcing frequency. That's pretty straightforward. Calculate the frequency of the infrared radiation of 3.3 micrometers. Well, 3.3 is your micrometers, is your wavelength. Okay. Wave speed is equal to frequency times wavelength. Wave speed is the speed of light. Frequency is what we want. Wavelength is 3.3 times 10 to the minus 6 meters. Rearrange for F, this is straightforward as that. Then it's saying, hence calculate the stiffness of the hydrogen chloride bond. Well, if you have frequency and you do 1 over the frequency, that's going to give you a time period. That then needs to go back into the expression from before. Okay, they've given you the mass, you know 2 pi is constant, so you rearrange for k. Okay, if you're a bit unsure of rearranging for k, I'll go through that with you right now. So t squared is going to equal to 4 pi squared k over m. So therefore k is going to equal to t squared m over 4 pi squared. Okay, so that's your rearrangement for k for that. Nice 11-mark question starts off. Question 2, a simple experiment that we've done in class many times. Okay, so the idea of mass oscillating on a spring, and they've drawn some graphs from it here. We've got a displacement time graph, followed by an acceleration time graph, and they want a velocity time graph. They want us to draw a velocity time graph. Maybe not straight away, but at some point. Determine the amplitude and frequency of motion. So you go to displacement time graph for this. Amplitude is how high it is from the center, okay, and the frequency is about, it looks about 0.2 on mine, but it's probably be slightly less on your graphs, which will be a bit more accurate than mine. If you actually know, if you look on this side, no, you see I'm not reading it from the correct line. Right, okay, so take the bottom line, take the top line, so it's about 0.8, and that's 1.1. So that's 0.3 0.3 of a difference, about 0.15, 0.16, maybe 0.17, that sort of region is what they're after in terms of that amplitude. So don't assume it's going right to the bottom, it's not, which is the mistake that I made. Take the difference, half it. Frequency, well, it starts at 0 and then goes to 1.2. That's the time period, so 1 over the time period gives you the frequency, so 1 divided by 1.2, and it gives you about 0.8. Okay, so the time period is 0.8, so the frequency is 0.8 hertz, and the amplitude is about 1.7 meters. Right, next. Show the maximum velocity of the mass is 0.9 meters per second. Maximum velocity. Well, we haven't got the velocity time graph. Okay, so the way you find that is by finding the gradient of this graph at its steepest. So that's over here. You take the gradient of that, it should equal 0.9. Yeah. So, next question. Oops, too far. Complete the graph, so as mentioned before, complete the velocity time graph for the same time intervals. Okay, right, okay, so at the same time interval velocity time graph. So time period must be 1.2. Okay, the time period must be 1.2 because the time period of each of these is 1.2, so therefore it's going to have a frequency of 0.8 hertz. You know the maximum velocity happens at these points here. So you can label these points as your highest points. Okay. So when this is at its 0 point, so not 0 along this line, it might be 0 along that line actually, yes it would be 0 along that line. So when that's at 0 along that line, you get a maximum acceleration, and that should be plotted against 0.9. So maximum negative over here, and maximum positive over here. Yep, and maximum negative over here. Just going to start this way, going down. Nice question to get for 2 marks. Define simple harmonic motion. Okay, the acceleration or the resultant force is proportional to distance, but remember it's proportional acting in the opposite direction. So A is proportional to minus x, or F is proportional to minus x. That's your idea. Describe how you can use data from the graphs of H, A, and T to check that the motion of the mass of a simple harmonic. Note that you're not required to actually calculate the check, so you don't need to do the actual calculation, but you can describe what you actually do. So what you do is you read a value of H, okay, and that's your displacement, and you'd plot an acceleration displacement graph, or you look at your ratio of A divided by X, and A divided by X should remain constant, or if you did H against acceleration, or acceleration against, if you had an acceleration displacement graph, it should be a straight line. That's your idea, okay? Or if you did acceleration minus displacement for any of the points, that should always equal a constant. Okay? That's how you check it. And the value of, you need to plot for minus displacement to end up with a positive gradient, otherwise you end up with a negative gradient. A against X would give you a negative gradient, a negative constant gradient. A against minus X will give you a positive gradient like such. Because remember, A is proportional to minus X. The reason why is F is proportional to minus X. Remember, F and A are proportional from Newton's second law. Okay, question number 3. Go for that last question, that last format question again if you need to. It's quite a tricky one. The idea, remember, to take into account is A is proportional to minus X, and the reason why is because F is proportional to minus X. So if F is proportional to minus X, F and A are directly proportional because of Newton's second law. So if you plotted a graph of A against X, it'll have a negative gradient, or A against minus X, it will have a positive gradient. So when a person walks on a suspended footbridge, the bridge can oscillate with increasing amplitude. Name the effect. Same question as always, resonance. But it also says this time state the condition for the amplitude to increase. Remember, natural frequency needs to be equal to, driving frequency needs to be equal to natural frequency, or the step frequency is equal to natural frequency. So it's called resonance, this idea. So the wind in 1940, I think I've shown you this video, the Tacoma Narrows in the United States. In 1940, the wind caused some alarming movement and twisting of the bridge. the amplitude of the oscillations became so large that cars were abandoned on a bridge. Why can these oscillations be described as forced? The idea is because they're being driven by the wind. The wind is what's blowing on the bridge, causing the bridge to actually experience these standing waves to be set up on there. If you don't remember the video, just type in bridge Tamako Narrows into YouTube and you'll see the video. It is pretty amazing to see what happened on the bridge. If I remember correctly, cars were abandoned on there, one which contained a dog, and unfortunately the dog was too scared to leave the car and ended up perishing, which must have been quite a horrible experience. So the vertical oscillations of the bridge can be modelled using the equations of harmonic motion, so the ones in the sections above. Calculate the maximum acceleration of the bridge when it's oscillating at 38 times per minute, when the amplitude, maximum displacement, the maximum amplitude was 0.9 meters. So A is equal to minus omega x, or minus omega squared x, or minus omega squared a, or just the idea of the maximum acceleration is going to be equal to omega squared times by the displacement, whatever that may be. And also the idea that we're going to use is omega is equal to 2 pi over t. So first we need to figure out the time period. Well, the time period for this situation, if it's 38 times per minute, we want to know how many of these take place in 1 minute, essentially. So how many of these take place per second? So 38 times in 1 minute. So it's going to be 0.63 per second. So that's how many revolutions there are per second. So T is 1 over F. We've written all of this down and you can't see a single bit of it. Apologies for that. Let's zoom out. There we go. T, let's make the webcam bigger for this bit, is equal to 1 over F. So they're the expressions that we're going to use. Well, our time period is 0.63, so our frequency is 0.663 hertz. And the reason why we know that is we did 38 divided by 60, so that tells us how many oscillations there are per second. So that's going to be 0.63 reoccurring. If I did 1 over that, that tells me my time period. 1 divided by answer. So that's about 1.6. My time period is 1.6 seconds. I can then do 2 pi divided by my time period to give me my omega. 2 pi divided by 1.6, which gives me about 3.9. Let's just say. That 3.9 then goes into the next equation. 3.9 more. And then we times that by the amplitude. I'm just going to check to see that the amplitude is 0.9, not the maximum displacement was 0.9. The amplitude oscillation is 0.9, correct, yeah. So you end up with about 14 as your answer. Let me just double check I haven't made any silly errors. Yeah, no, I haven't. That's brilliant. So 14 meters per second squared as our answer. Okay, so it's working through those 3 expressions there. And remember the frequency we figure out by doing 38 divided by 60. Okay. Use this value to explain why an abandoned car on a bridge would lose contact with the road surface at a certain point in the oscillation. Identify this point. Okay, so A max is bigger than G. Okay, so if acceleration is greater than gravity, it's going to accelerate at a greater rate than gravity does, and therefore it will come off the bridge. So the calculation we've got to do is to actually figure out the displacement that's going to cause this to happen. Because they want the point at which it's going to come off. Well, A is equal to omega squared x. So if we rearrange for x, so if we rearrange for x, we end up with A over omega squared. When A is equal to G, it will just stay on the bridge. When A is greater than G, it will come off the bridge. So let's figure out the point at which it sticks on the bridge, and anything greater than that, it will come off the bridge. Okay? So if we did the acceleration, so the acceleration we want to use here, we want to put A is equal to G in. So we want to put in, if it was accelerating due to gravity, at what point would they match, essentially? And our omega is our omega from before, which if I remember correctly, I've written down, which is about 13.9 squared. Okay, so if we do that, 3.9 squared, sorry. So if we do that, we end up with a value of about 0.6. So 0.6 meters would actually detach. So above 0.6 meters, it would detach. So a value greater than 0.6 meters, that's when it loses contact. Okay. Again, tricky question. Work back through that one if you need to. Right, a mass hangs on a spring suspended from a fixed point. When displaced and released, the mass oscillates in the vertical direction. Describe how you can determine accurately the frequency f0 of these oscillations. You may be awarded a mark for the clarity of your answer. Okay, so it's pretty straightforward. You first need to figure out the time period and do 1 over the time period to figure out your frequency. But you need to start listing the apparatus. So you've got to state the apparatus you need: clamp stand, retort stand, boss, clamp, spring, mass, G clamp. Okay, so you've got safety precautions in there. Stopwatch. Okay, remember you need to take the idea, include the idea that it's going to be the time taken for multiple oscillations, not just one. You could use a motion sensor instead of a stopwatch. You could use a light gate or a data logger. You could use a video camera, okay, any of those ideas, or you could use the strobe lighting techniques. But you've got to go through how you accurately measure the time period and therefore use that to figure out the frequency. Safety isn't the biggest issue, okay. You've really got to talk about accuracy of measurements, because that's what we're on about, determine accuracy. So using multiple oscillations, talking about using the strobe technique or recording it, or by using the idea of a data logger or light gates or a motion sensor or something along those sort of lines. Okay, so we've got a setup over here of a mass and a spring. This time it's connected to a vibration generator. A short time after the vibration generator turned on, the mass settles down to perform simple harmonic motion at the frequency of the generator. Label the axes and sketch a graph showing how the amplitude of this oscillation changes as the frequency is varied up to and beyond f0. Mark the approximate position of f0 on the frequency axes. Okay, so you're going to end up with a graph. So you're going to change frequency and scale amplitude. A graph that looks like this. Okay, so have that sort of graph to it. There's your f0, and that's A max. Sorry, capital A max. Maximum amplitude. Right, next, state and name the phenomenon. Actually, I'm just checking over all the marks for a previous question. Yeah. Yeah, as long as you label your axes. Right, state name of the phenomenon illustrated by a graph. Resonance. This phenomenon can cause problems in the design of footbridges. Explain why. What I was just mentioned in the last couple of questions. If there's wind blowing or if people walk on it, it could force it to vibrate, and that resonance could cause large or violent oscillations on the bridge. Okay, large, dangerous, violent oscillations on the bridge. I'm just going to check to see how many more are still on this one. Yep, there's a couple more questions still on this. Right, water molecules oscillate when stimulated by high frequency electromagnetic waves, and a microwave oven heats food that contains water by force of water molecules can vibrate at their resonant frequency F0. Explain what is meant by resonance, suggest what a microwave frequency chose to be F0. Okay, we've been through this question a few times, similar sort of things. Natural frequency is what F0 actually is. If it's at F0, they vibrate with a maximum amplitude, and therefore it is maximum amounts of energy transferred. Okay. So we've got a few ideas here about efficiency of heating meat. So microwave oven is used to heat 1.2 kilograms of meat. The temperature of the meat increases by 75 kilograms in the first 10 minutes. The power of the microwave is 800 watts. Calculate the efficiency of the heating process during this time. Take the specific heat capacity of the meat to be 3,200 joules. Now, you might not have done thermal physics yet. However, in GCSE physics, we now cover the idea of specific heat capacity, so you should be able to do this from the equation of E equals mc delta theta. Once you've used that, you need to do it divided by, so to get this into power, because that's going to be divided by time, this needs to be divided by time as well, but the time is going to be 10 times by 60, because you need to get it, so in other words 600, because you need to figure out how many seconds it's going to be done for. So you'd figure out what the power is by putting the values into this. You do that value divided by 800, that comes in, and then you figure out the efficiency. Why does the temperature of the meat not continue to rise at this rate for the next 10 minutes? Okay, because it's going to lose energy to the surroundings, or there'll be less water molecules actually inside there because it'll evaporate off. That's the main idea for the last part of that question. Question 6. Oops. So you had a car driver in the rear view, and she noticed the rear view mirror shaking particular a lot at a specific speed. Stop it shaking, sticks a big lump of chewing gum to the back of it. It's kind of disgusting, but it would work. It would make it stop vibrating. Which of the following statements is correct? Okay, it's no longer shaking because it's heavily damp. The mirror still shakes a lot at the same speed because the chewing gum is not changing the damping. The mirror shakes a lot at a different speed because the chewing gum has changed the dampening, or the mirror shakes a lot at a different speed because the chewing gum has changed the resonant frequency of the mirror. Well, what it's actually done is it's changed the mass, and if it's changing the mass, it changes the time period. If it changes the time period, it's going to change the frequency. So it's changing the natural frequency, the resonant frequency, because it's changed the mass. So the answer to that question is D. Okay, and that brings us to the end of ISP task 1. Thank you very much for listening, guys.